Students have a battery of EMF E with negligible internal resistance and many identical resistive heating elements, and will connect the circuit so that the heating elements can be used to heat some water. Each of the heating elements has resistance R. A. First, the students consider connecting the heating elements in series with the battery as shown above. One student says that to heat the water faster, they should use as many heating elements as possible. 1. Write an equation for the power P dissipated by a circuit containing N heating elements in series in terms of E, R, N, and any physical constants as appropriate. And then 2. Does your equation support or refute the student's claim about the time it takes to heat the water? Justify your answer. Before we dive too far into it, really want to stress here, they want answers in terms of these symbols. So those symbols and only those symbols. And they're probably looking at things like epsilon naught or whatever for the constants. But that's kind of boilerplate. They always say physical constants as appropriate. All right, so if we want to do this, we might want to replace our circuit with an equivalent circuit where we have one, let's call this, I'm going to call this RA for part A, where we have one resistor, because then we could compute the current that goes through based on the EMF that we have. To do that, of course, we need to figure out the equivalent resistance RA, which is going to be R plus and so on, and it's going to happen N times, so we're going to get that the equivalent resistance is N times the individual resistors, because in series they just add for resistors. All right, we could find the current by saying that doing a Kirchhoff's loop if you want, E plus the current drop, the potential drop across the N resistors. And we should put a minus sign to indicate that its current voltage drop has to be 0, so that the current that you draw is the EMF over NR. And we might want to just go, the power is, of course, generally V squared over R, right, as a general thing. Actually, we can do better than that, though. The power is just going to be V times I. So we're going to get the EMF times the EMF over N times R, or EMF squared over NR. That's part 1. Part 2, it refutes the student claim, because as N increases, power decreases, less energy per second. Oh, wow, that's, even for me, that's pretty bad. Power decreases, so we have less energy per sec. Let's do it this way. Fewer joules per second. Takes more seconds to get a particular temperature rise. Part B. Another student suggests that connecting the heating element in parallel might be a better idea. The student says that a certain number of elements in parallel heat the water faster than the same number of elements in series, because the current in the parallel circuit will be less. Part 1. Write an equation for the power P dissipated in a circuit containing N heating elements in parallel in terms of E, R, N, and physical constants as appropriate. And again, just to stress, our answer has to have only those things in it. So if we go sort of up here, well, now we have, if we call the equivalent resistance RB, we know that 1 over RB is 1 over R plus 1 over R plus 1 over R plus so, and we do this N times, so 1 over RB equals N times 1 over R, so RB equals R over N, which makes sense because, of course, remember, it's always less resistance in the parallel circuit than any individual resistor. All right, then we can say again that by Kirchhoff's loop, we have E minus IRB is 0. So I is E over R over N, or NE over R. And so the power, which is VI, is the battery's voltage times N times E over R, or N E squared over R. All right, part 2. This supports the power in case B is much greater than the power in case A. Whoops, better if I wrote it correctly. The power in case B is greater than the power in case A because N is greater than 1 over N. Sort of duh, but more joules per second with parallel case. And then I guess we'll go over here. And we're in case 3, or question 3, and the student is incorrect. I accidentally found that in case 1, the current was E over NR. In case B, it was N times E over R. So again, we see the current is actually larger in this case than the other case. So even though the student had the right sense of what to do, they were wrong as to why it would work.